Hey, what's up, guys? Chung here again. And so this time, let's take a look at this LeetCode problem, uh, number 1140, Stone Game number 2. Alex and Lee continue their games with a pile of stones, represented by an array of integers. And each of them will pick the stones in turn. And the game continues until all the stones have been taken. And the problem is asking you to return the maximum stones Alex can pick, assuming both Alex and Lee will play optimally. And one other constraints or conditions for this problem is that there's like limitations of m that re that constrain you how many stones you can take at each round. So the range of stones you can take is from 1 to 2m. And once you finish picking up the stones, you need to update. Basically, the next person can use a new range to pick up the stones for him. And the new range is either is from the maximum value from the previously m or the new m or the x. So what does it mean? It means that, let's say, for example, if let's say the x is 4, if x is 4, the range for person A is from 1 to 8, right? And if this person takes the piles from 1 to 4, then the next person, the the range for next person is also bounded with 4, right? But let's say if the current person takes 6 stones, 6 is greater 6 piles of stones, and 6 is greater than the 4 than the 4. So that which means the next person can take 1 to 2 times 6 is 12, right? Okay, so that that's what this problem is all about. And this is another classic minimum maximum dynamic programming problem. So with this minimum and maximum dynamic programming, so first there are two players. Second, each one takes turn. Third, everyone plays optimally. And the the algorithm for all this minimum and maximum problem is that for for current DPI, right? Instead of calculating which instead of check which player is playing, we simply convert this problem to the maximum winning number at this current position of I, starting from this position I. So at this position I, we're assuming no, it doesn't really matter which player is currently playing because I, either player will both try to optimize their scores, right? So that's why at this DPI here, we just need to know what's the what's the maximum winning number. So by winning number, I'm talking about the per the scores for A. Let's say we have a and B player, and at this position, A is the one who is playing the game, the picking the piles. So we're trying to say find the the maximum result of the current player A that can be that can get how much more the A can get comparing to B, right? So for that we have to do this, and basically we're gonna do a max of all the possible ways that the A can currently pick, right? So it's gonna be the sum of I to I plus K, right? Assuming K is there are K ways the current A can pick, and minus dp I plus K, right? So yeah, basically that's our dp state transition function. At the current I here, we try all the possible ways that A can pick, because A can pick case the first case stones, right? And after that, we'll be handing the game over to the B, right? So the B will be starting from I plus K, right? And among all of those scenarios, we get the max one. And in the end, we have a dp0, right? dp0 tell us at the beginning, right? That's basically our result here. At the beginning, what's the maximum winning number for A here, right? So, and since it asks us to get the value, the total points of A, so with this maximum winning score, right? We can we can get the total number that A can get, right? How? We just use a total. We use total. We use total of the piles here, and then we plus this maximum winning number, right? For example, this one here. So the total is 26, right? And if you're following this DP problem, the maximum winning scores for A is -6. So the -6 means no matter how hard or how good the the player A is trying to play, the best winning score he can get will be -6, which means player A will get 6 less stones than player B, right? So with that conditions, we can simply uh, conclude that the stones player A gets is the total plus -6 and divided by 2, which is 10, right? So that's our result. And if we want to get the other persons, we simply use the 26 divided by 10, right? Then it's going to be 16. So player B in this case will get 16. And right, and since you guys see here, so the condition, the DP problems, right? So this problem like relies on the future result, right? And if we want to do it from the bottom up way, so which means we have to calculate from the end first, right? But the problem for this the issue for that approach is we don't know the m when we get to the last, right? Because m depends on the previous one, right? So for that we have to do a top down, so that because we start from 1, we start from m equals to 1, and then every time when we uh when we finish calculating the current I here, we update this m and we pass it to the helper function or the DFS function. And if you guys remember, there's another similar problem called Stone game number 3, right? So for that problem, so it's actually it's kind of even simpler in a way, because in the Stone game 3, one person it's a basically this k is a fixed length. The one person can only pick 1, 2, or 3, right? Because of that, okay, so because of this length is a fix, then we can try to do either bottom up or top down. Because for the bottom up, we can simply calculate from the last element, and then we're moving back to the beginning. Because we know at any point the k there's only 3 possible ways for k, either 1, 2, or 3. But with this stone 2 here, the k could be it based on the previously k, the previously x, or that's why there's no way we can do a bottom up DP. We have to do a top down. Okay. So okay, with that being said, let's try to code up here. Okay, so since we're doing a top down, we'll be needing a DP helper functions here, right? And for each, the state will be the current position plus the current m, right? So that's the state. Basically at this position, at this current position, what's the m, right? The m will be telling us what's the range we can take, the current player can take from 1 to 2m, right? So we'll be having a few variables here. For example, the memorizations thing here, right? So it's for all the DPs here. And so if in mem we return I am, right? And if I is greater than n equals to length piles. So basically, if the I is greater than n minus 1, right? Then we know it's out of the boundaries. We just simply do a return 0. Okay. And okay, so then we have a loop here, right? So we're gonna define the answer here. So the answer is gonna be since we're getting the maximum value, right? So we're gonna define like system dot max size, all right? Minus, and then we're gonna have a loop here. So what's gonna be the loop? So I'm gonna use a k here. The k is in range 1 to 2 m plus 1, right? So that's the range that we can pick with the current m, right? From 1 to 2m, because the closing is inclusive. Sorry, it's exclusive. That's why we need to do a +1 here. And among all of those possibilities, we're gonna do a answer dot answer. Gonna do a max, right? So yeah, since we're going to get calculating the pre-sum, right? The sums of basically a sum range here, and we'll to speed up the calculation, we need to have like a pre-sum arrays or the dictionary. So for me, I prefer using a dictionaries because I can add a -1 0 to it. And then I'm gonna calculating this pile in enumerate piles pre-sums dot I equals to the p plus pre-sums I -1. Okay, so then we'll be having this pre-sums. So with this pre-sum, we can it's easier, very easy for us to calculate the the range sum. So the range sum now will become the pre-sums uh, I plus k, right? I plus k -1 because we're doing the current one. Since if we're picking because at the beginning I is the ones we start, right? And the case it means the numbers, the piles we're trying to pick, and 1 means we're going to pick the current one, which is I, right? That's why the starting sum for our is the gonna be the current sum, right? I plus k -1, and then minus the pre sums is gonna be the I -1, right? So that's how we get the current piles this current player can pick. And once the player has picked the current pile of stones, the game will be handled to the next person. That's why we'll be doing a relative sum, a relative maximum value between the current ones and the ones the other person can get. So the other person how much the other person how many stones the other person can get. It's in the dp I plus k. That's where the second person starts, right? And how about the m, right? So the m will be the maximum of current m and the k, right? That's how we define the next level of m, right? And then okay, and then once we are finished calculating this, I'm gonna to assign this memorizations, right? This answer to the current memorizations to the answer, and I simply return the answer here. So one thing we need to be noticed here, so these things could be out of the boundaries, right? This k here, it could be out of the boundaries both in the DP and in the pre-sums, right? Because the range will be greater than the n here. For the DP, I think it's better because we have this function to restrict that to check as if this I plus k, which will be I in here, is greater than n minus 1, we simply return 0. So for this part, it's fine. But the pre-sums, right? The pre-sums I plus k minus 1 will definitely be out of the boundaries, right? So that we're gonna do we'll do a simple check here. Basically, we're gonna do a minimum of the current I plus k minus 1 and the n minus 1. N minus 1, yeah. Because the n minus 1 will be the last element in the pre-sums. Okay. And cool. So then we just need to check 0 and 1, right? At the beginning, uh, the index is 0 and the m is 1. So this thing will give us the maximum winning number, winning scores, right? For the first person, right? What did that? The indentation is not. Oh, I think here. Sorry. This one. Yeah. So yeah. So this maximum winning number, winning scores, which it basically means that how many more scores the person A can get than the person B, right? And then we simply do a with this offset relatively score, we can get the actual score of either person A or person B. In this case, it's person A. So that's why we do a total sum. So the total sum is already there. We just do a sums n minus 1. So the last one in the pre-sums will be the total score, the total stones in the piles, right? And we plus the max winning scores, right? And then we just divide it by 2. So that should just give us the result, pre-sums. Okay. All right, let's try to run it. Yeah, so passed. And I think a small improvement we can make here is that, so the precondition for this improvement is that all the stones are positive values. So with that constraints here, it means that, let's say, if the range this currently person can pick is greater than the remaining stones, right? In that case, we don't have to try this pre-sums and this one by one, because we know for sure that person will definitely take everything, right, left, because that's definitely his best his optimal play strategy, right? So what I'm saying is that, like, 1, 2, 3, 4, 5, 6, right? Let's say at this position 4 here, right? And the m equals to 2, right? So how many piles of stones we have? 1, 2, 3. We have 3 left, right? And the picking range for m is 1 to 4, right? 3 is within 4, which means at this point the person will definitely take everything, right? So with that said, before doing this for loop here, right, we can do a simple check here. Basically, if the mm, if the remaining stone is the n minus I, right? Yeah. If n minus I is is within the range of 2m, right? Then we can simply set the answer to to everything, to the sum of the remaining range, right? So it's gonna be the pre-sums of the n minus 1 minus pre-sums I minus 1, right? else we do this. Okay, so let's try to, I think it should be faster. Yeah, I think it's much faster because if this m becomes pretty big, right? And let's say the m becomes like 100 or something. Yeah, it is 100. Then we can save, and this I we have like 90 or 80 left, right? Then with this m with this m within the like within 200 or 100 range, we can just simply skip all the 100 or whatever left in that in the pile of stones. We can save all this DP recursions for that. We can simply return it, right? But that's the only in the constraint in the conditions of all the piles of the stones are positive values. If they're like either a positive value or negative values, like the case in the stone game number three. Yeah, in stone game number three, the stone values it's in the could be the positive, and it could also be the negative value. In that case, we cannot use this shortcuts because we don't know if there's like any negative values in there, right? Because if there's negative values within the range, we're not sure if this is the optimal uh, approach, right? In that case, we have no other choice but to try this some the scenarios one by one. Okay. Mm, yeah, I think that's it for this problem. Yeah, another very classic problem for stone games. There's like stone game 1, 2, and 3, and in total, I recommend you guys do all of them together so that you have a better understanding about this kind of minimum and maximum DP problem. So we always use this relatively maximum score for the current persons, and based on that, we'll do some calculations in the end to give us the final answer. Okay, cool guys. I think that's it for this problem. Thank you so much for watching the video. I'll be seeing you guys soon. Bye bye.